My job here is to make you all kind of experts in Garden 4's semantic spaces, conceptual spaces, in about 7 minutes or less. I'm more or less going to be James's hype man for this talk, and then James is going to take you through all the nice graphical mathematics. So let's start. Do you all see this? Okay, now look at this and ignore the shape for a second. Just look at the color. All right, if you can see it, take a look. All right, I'm going to show you something else. Hold on to that in your mind. Listen to this note. Do you all hear that? Okay. So here's a somewhat tricky and difficult question. What does that color and that musical note have in common? And this is why Garden 4 is supposedly, a very clever person. So give you a second to think about that, but it's kind of tricky. So let's give the question a little more structure. So color, okay, we can break down color. We kind of know that color is made up of a hue and a brightness. And what about musical notes? Well, you know that musical notes have a pitch and they have a volume and they have a timbre, and the timbre is sort of like the texture, so you can kind of tell apart the same note played on a trombone and a violin. And just by breaking it down into these qualities, we can see that we can already impose some geometric structure. So we call each one of these qualities that I just mentioned a quality dimension. That's a term. And so for color, well, maybe you want to represent hue as a sort of flat circle with all the hues that you can get on it. And maybe brightness is just kind of a line going from totally dark to totally bright, and it's just white. So you can put the line orthogonal to the circle, and so color space ends up looking like two cylinders kind of stuck together. So you have a flat circle, and if you go all the way to black, then that kind of just tapers out into black, and if you go all the way to white, that kind of just tapers out into white. So maybe here's a partial answer to that question. These experiences are points. So experiences are points in some geometric space. And if you want to talk about different properties, like say yellowness or greenness or F sharp, you can call them kind of regions of geometric space that you would go, yeah, that's kind of yellow, that's kind of a green, or that's kind of an F sharp. And that's Garden 4's big idea. The big idea is that, okay, there's got to be some kind of missing link between raw perceptual data and symbolic representation, like when we say yellow or green or F sharp. And he says, okay, geometry is the missing link. So take the raw data to be points in some geometric space, and then we take regions in those spaces to be symbolic properties. And these are Garden 4's conceptual spaces. So remember I said, look at this banana and ignore the shape. Now, how was I able to say that? Look, if it was a very big banana, you could just, just put it all the way up here. You could experience just the color and not the shape. But here's the second sort of half of that question. It's impossible to experience hue without brightness when you're looking at color. Just like when you're listening to that note, it's impossible to just hear the pitch without also hearing a volume and a timbre. So that's another partial answer to this question. See, color is made of integral quality dimensions, hue and brightness, which is to say you can't experience one without the other, just like pitch and volume. So, for example, let's take taste. If you have taste broken up into different quality dimensions, sweetness, sourness, saltiness, bitterness, umami, in whatever geometric form you want to stick them in, that's an integral altogether. That's an sort of integral, those are integral dimensions, because you can't get one without the other unless you damage your tongue. Okay, so you're now experts in conceptual spaces. The hardest part actually was probably just coming up with that terminology. Quality dimensions, integral and separable dimensions. Separable meaning quality dimensions that you can experience separately. Integral meaning those you have to get together. Once you have all of that and the idea that you want geometry as the mediator, then you kind of get it. The rest you can kind of guess and think about by yourself, and you won't be too far off from what Garden 4 thinks. So now, onto the main talk. Right. So there are two problems that we want to face here, because we want to do some sort of semantic engineering. So first, all right, you have free reign of what geometries you want to model these quality dimensions. Suppose you have that. Now, how do you deal with properties that change over time or throughout the text? Like, for example, a chameleon changing color. So what's up with that? Okay, well, you might say that there's some sort of chameleon space concept. How do we even construct something like that? Well, we know that color space is going to be somehow related to chameleon space, and they've got to interact in some way, because I can tell you that a chameleon is red and then green and then red, and you can kind of picture that in your head. So what's going on? What tools do we need to model that, the changing of properties and sort of possessed properties of concepts? So that's the first question. And the second question is, okay, what about fruit space? If you look at this banana again, like, okay, let's say that fruit space is something like you got color and you got taste. Those are individually integral, but together they're separable for most things. But when you look at this banana, you can kind of guess what it tastes like, right? And if I show you this other banana, which is slightly greener, you can also kind of guess what that tastes like. You can kind of think that the yellow banana is going to taste a bit sweet, the green banana is going to taste a bit bitter. And so you can choose whatever geometries you want to model color and taste. But then how do you start modeling banana space? Well, we can call bananas, say, a region of fruit space, but there have to be some correlations. They're not really independent, because you were able to picture what that banana tastes like based off the color. And if you close your eyes and ate a banana, you could have a good guess as to what the color of that banana was. So somehow they're not independent. And this region, we want to build these regions, banana spaces, a sort of subgeometry where you take previously separable quality dimensions and you kind of blend them together. And so you have this subgeometry where these two things are now no longer independent. And now we have one story for both of these problems, and we call this story update structures. And it follows by some very easy graphical mathematics based in, the category theory and string diagrams. Even if you don't know any category theory, you can kind of get these diagrams just by looking. And so using these update structures, we're going to build towards categories of concepts. And that's the hype. So James, take it away.
Yeah, cheers, Vincent. Let me just share my video and screen. Where are we? Hopefully people can now see my presentation, I hope. Yeah, so thanks, Vincent, for the introduction. I'm going to dive a bit deeper into what we actually did in our paper. So as Vincent mentions, there were two main goals. And I think the best way of maybe reiterating these goals is by direct example. So we can imagine that we're reading some text, and this text could be about Cam the chameleon. Here's Cam. And as the story progresses and Cam goes through his life, we find out that he's able to change his color, and he changes from being green to red. And in the language of Disco Cat, we might represent Cam as some wire, and then we'd need some box that allows us to model this color change. And our first goal was to ask, well, what should this box be? What things could we pick for this box? And in general, we could imagine lots of circumstances where we have some system, and in this case, our system was Cam, and we have some properties, in this case it was color, and we want to sort of update the properties of this system, and what should these boxes be? And then our second goal was, well, once we have a bunch of these boxes, say we have a box for the color of Cam and for the mood of Cam, how might we be able to combine these together in some non-trivial and interesting ways to get new boxes? And indeed, one can imagine that maybe Cam's mood influences his color, and we might want to in some way be able to capture this extra data when we do this combining. And we'd like to be able to model these circumstances. So maybe a first attempt at coming up with an update for color. If you know a little bit about categorical quantum mechanics and Disco Cat, one might try a spider. They seem like a reasonable suggestion. And we can imagine Cam here, and he updates his color, he changes to be red, and then he changes to be green at some later time. We do this by taking some spiders and plugging some states for red and green into them. But this comes with a sort of a serious problem almost immediately, and that's that spiders commute. So I can just pull these spiders through each other, and I get this diagram. And now Cam seems to be changing his color to green and then red, and we've lost all the causality of the story we're telling. So this really is not ideal, and spiders in this way don't seem to capture this particular type of updating. So spiders are not suitable for all styles of updating. I mean, indeed, there will be some circumstances where they're precisely what you want, but here's an example of one where it really is not ideal. And indeed, these sorts of issues have been considered before. Bob and Konstantinos wrote a nice paper on meaning updating of density matrices, where they suggest using doubly mixed states as a possible update method and to get around some of these issues that I speak of. And our first aim is very much sort of aligned with this. But we wanted, first of all, to ask, well, what does it mean to be an update? I keep using this word update. What do we actually mean by this? And can we give some axioms that would allow us to pin down what an update actually is, and to have some bar by which we can judge whether something is an update? So we suggest the following, and that's that an update structure ought to come with two boxes, a put and a get. And this put box takes a system S and a property P, and it applies the property P to the system S. So it updates the system with this new property and returns the system. And then the get box sort of does the opposite. It takes the system and it reads out the current property, leaving us with the system as well. And then these boxes ought to have some laws that constrain how they interact. And we were very much operationally motivated in how we picked these laws. We came up with the following set, and we felt there should be this put get law, where if you update with a property and then read out some property afterwards, well, this should be the same as some pre-processing on the properties and then updating with one of the copies. So you could sort of imagine this map here as being the copying of the property, and I update with one of the copies of it. And then there's the get put law, where I read out a property and then put it back in again. Well, this shouldn't do anything to the system. And then there's the put law, where if I update twice, it should be the same as doing some pre-processing. So for instance, mixing the properties in some way, and then updating with this only once with this new mixed property. And then there's the get law, which is sort of the opposite of the put in some sense, where you read out the properties twice, and it ought to be the same as reading out once and then doing some post-processing, so copying, for instance, of these properties. Now, I should stress that I've been using the words mixing and copying here to describe these maps that I've drawn like spiders. We actually don't make this assumption, not in that we don't assume that they are full spiders and therefore that they're special commutative Dagger-Frobenius algebras. In general, we just allow these to be any maps. And it turns out that by weakening this structure from being full spiders, there's actually some quite interesting examples that are sort of weaker than spiders. I should also point out that our choice of names for all these laws and boxes is not completely by accident. We're very sort of inspired by the work people have done on lenses, in particular very well-behaved lenses in Cartesian categories. And these typically come with a couple of maps that put in the get that are quite similar to ours, and then three laws that are again quite similar to ours. But there's one kind of notable difference, and this was an issue with just trying to lift this directly to the monoidal case that we're working in, and that's that the get map is sort of in some sense of the wrong type. It takes a system and it just returns a view, it just returns a property, and we've kind of in some sense destroyed the system's no longer around, which wasn't really what we wanted. And indeed, this isn't an issue in the original setting of very well-behaved lenses, because in a Cartesian category, one can freely copy any types. So essentially, if I want to keep a copy of S, well, I just copy S first and then do the get. But of course, in a monoidal setting, I can't freely do this in the same way. I can't just copy quantum data, for instance. So we felt that our get box ought to return the system as well as a property. And then if anyone who's interested in more of the actual details of this, there's a follow-on paper we wrote that deals with some of these issues in a bit more detail. Okay, so maybe a toy example of these sorts of structures, it would be good. So imagine the aforementioned banana that Vincent had earlier, and here's an artistic interpretation of one. And bananas are typically either green or yellow, and they taste either sweet or bitter. And thus, we could imagine trying to model a banana as a pair of a color and a taste. And then once we've done this, we can construct the put, the get, and a mixing map on these, where the put just updates the current color of the banana with a new color, and the get sort of retrieves a copy of the color. It's a very simple example. And then the mixing map just sort of deletes the left hand, raises the left hand color. And one can check that these do satisfy the laws that I gave earlier. But there's kind of a little bit of an issue with this model, and it's not as rich as it could be, and that's in part because we know a bit more about bananas. I mean, yellow bananas are typically sweet, and green bananas are typically bitter, and we don't have sweet green bananas. I mean, a sweet green thing isn't a banana. So modeling a banana as all possible pairs of colors and tastes is not quite the right thing. How do we then deal with this? And our idea was to introduce another box. We call this box the correlator, and this takes properties and it kind of contains extra information about how these properties influence each other, how they're associated with each other. And we demand a couple of things of these correlators. Firstly, that they're idempotent, so that if you correlate something once and correlate it a second time, well, it's the same as just doing it once. And that they are basically a magma homomorphism, so that they are kind of copied by the copying map. I can pull them through these spider-like maps. And then once we have one of these correlators, for instance, we can imagine this is the correlator for bananas, and then all the states that are bananas, the other states that represent bananas, ought to be consistent with this correlator. So if I take one of these states and apply the correlator to it, well, I should just get back the state. And similarly, all the transformations, all the transformations on bananas ought to be consistent with the correlators. So there's a nice categorical way of capturing this circumstance, and we can move without going into any real detail about how this works. We can move from working in the category we originally into its Karubi envelope. And with a little bit of hand waving here, one can imagine that the objects of this new category are in some sense the correlators themselves, and that the maps between them are precisely the maps that are invariant in the way that I've given here. Okay, so returning to our toy example, we had this bijection between the color and tastes of bananas. And of course, this induces the obvious map from the set of colors to the set of tastes. And with this, one can construct a correlator, and it's precisely the one that picks out the yellow sweet things and green bitter things. And then once we have this correlator, we can, by doing this Karubi envelope construction, move to a new category where, in some sense, this correlator is an object. And now we could, for instance, associate bananas actually with these objects. So what we've been able to do is to construct a derived concept from some base ones. So here we had the base properties of color and taste, and we constructed a derived property of a banana. And in general, this sort of process iterates. So I could imagine having this banana, which is in this sense derived from color and taste, and I could have another concept around I don't know, the mood, and then I could have some correlator that says that people are happy when they have a banana, and by this construct a monkey or something. So now an interesting question to ask is how does our story of update structures and correlators play together? So we could suppose we have a an update structure for color, and an update structure for taste. Can we combine these together in some interesting and hopefully non-trivial way? We could try this. We could try plugging them into each other in this way, but up to the correlators. And in this sense, this would be sort of an update of now banana types in the Karubi envelope. So you can imagine these correlated wires as the banana types, and now we're sort of updating bananas on the system instead. And does this form an update structure? And you can check the axioms and find that it satisfies 3 of the 4. So it's almost an update structure, but not quite. And in fact, it does satisfy an additional law, which I won't go into the details of here. There's obviously more information in the paper if people are interested. But it's enough for us to consider this to be what we call a weak update structure. But it's worth looking at what goes wrong with this get put law here. And essentially, you end up with this correlator sandwiched between all the gets and the puts. And this kind of means that we can't reduce this diagram down any further, and kind of most certainly not the identity map. But when you think about this a little bit more deeply, this is kind of to be expected, really. I mean, if I take any random system and read out the colors and the tastes, there's really no reason a priori to expect that they should be correlated in this way. So indeed, the correlator may act in some non-trivial fashion, and there's no hope of this being the identity. But it turns out, though, that the axioms we've given are enough to guarantee that this get-put map is an idempotent. So in this way, it exists within the Karubi envelope category. So what we can do is now move from the system S originally to the system S prime, where we've done these get-put maps. And in this way, we sort of demand that the properties inside the systems are already correlated in some way. So they're not just random colors and tastes, but they're colors and tastes of bananas. So we kind of actually are putting the derived concept inside the systems in some fashion. And now on this object in this category, the structures I've given here do indeed form a full proper update structure. Okay, so the outlook from all this. We don't know how necessary and sufficient our axioms are. We were operationally inspired by how we picked them. We don't know if there were other axioms we could have picked, if there's some set that is in some way canonical. This is all interesting stuff to look at. We was, of course, interested in actual applications of this to various interesting tasks, and we've made some progress with this in our follow-on paper. We've come up with some other interesting update structures in there, but there's still a very large zoo of possibilities to explore. And then the final thing that I think is very important is looking at the composition of update structures. So I've given sort of a notion of how they might compose during this talk, but this is very much in contrast to how composition works for very well-behaved lenses. And we think there might be more than one interesting notion of composition of update structures, but typically they require different assumptions on the underlying structures that you have. So it'd be interesting to look at the details of how this all works out. So I'll actually leave it there and go to questions if anyone has any questions.